Okay, good morning, everybody. Welcome to Physics 4C, the online version. And this is spring of 25, so we'll see how we do. My plan is, my name is Marcus, I'll be your host. For this semester, my plan is to do classes every Tuesday, Wednesday, and Thursday, just about 9:30 to 10:50, this time block right here. And you're welcome to join live, as some of you are already doing. You're welcome to watch the video later, whenever convenient. The classes will be those 3 days. The labs will be put up on Fridays, and that will be its own kind of package deal. As to what's going on with the lab. So we'll have our first lab activity this coming Friday, after we've done our first 3 classes. So to this point, I guess, welcome, this is our first class. The Canvas page is up and will be modified during the semester. The syllabus is up. And it does outline, I think, most of the things that I want to get across. So maybe take a quick look at that to get an idea of what sorts of things we're going to do, what sorts of things I'm looking for, how things are, say, portions, like what we're going to have in terms of homework sets, what we're going to have in terms of quizzes and celebrations, what we're going to have in terms of PLCs. Since this is an online class, the PLCs will be all virtual. So just to get you up to speed on that, the class itself is 3 times a week for an hour and 15 minutes. And so we will take care of those. The lab is a 3-hour activity. I'll probably put up a video which kind of gets you going, maybe about the first hour or so, probably a little bit less. I don't want to do a whole bunch of talking. I want to leave the other 2 hours or remaining time for you to do the activity, write your results up, and finish that activity off. All of the labs will be submitted on Canvas, all of the homeworks submitted on Canvas, the quizzes and celebrations all given through Canvas. And so the honor system is what we're on here, okay? It will be, in this day and age, it would be easy to get a homework or get a quiz or something from someone else who's already started it, or look up something that has been done in the past, or ask someone online or something like that. So I am basically exhorting you, encouraging that you do your own work at all times. Unless it's a group activity, like homework is a group activity, that's fine. But straight off copying, straight off taking someone else's ideas, that's going to cause a lot more problems than they're really worth. So that being said, the only other piece to the class that I want to go over is the PLC part. Those of you who are used to PLCs, this will be a slight change. If you're not used to PLCs, this is what is listed in the catalog as the TBA hour, which is an outside of class, yet not strictly homework assignment. What we'll do, again, given on Canvas, they will be set up as quizzes where you'll go in and try to mark the right answers, and the program will grade what you have. I'll put the answers in, it'll grade it. If you need to go back and change something, you'll get another 2 more attempts after your first. So a total of 3 attempts on the quiz. But I don't want to call it a quiz. It's just that Canvas is going to call it a quiz. And so it's going to be set up in that format, but it's an activity that you are supposed to think of as not being part of class time and not being part of homework time. It's an extra TBA. That's what the TBA hour is. So that is whenever you have the time, you can log in and do that quiz on Canvas. But I am gonna assign one a week, and they are due by the end of the week. The one that's going this week, I am still trying to shoehorn into a quiz style format. So this is taking a little bit of extra time, but it will be up by today. So no, there won't be a time limit. The amount of time I said to be maybe to go into the activity with, probably about a little less than an hour. It's supposed to be about a 50-minute activity. Some will be more, some will be less. It's going to be kind of working out on the average, but nonetheless, hopefully if it's more, it's not double or triple or right. It shouldn't be more than, it shouldn't be significantly more than an hour. It may be 30 minutes, might only take you 30 minutes one week. That's fine. It's not a situation where we need to track the hours. It's just a situation where we need to track the submissions that you provide. So that's all part of the grade and the grade breakdowns in the syllabus and all that's good stuff. So we're here now. I think that's most of the stuff that I want to say about the formatting of the class. This is going to be essentially what you're going to see during the lecture hours. I'm in the classroom right now. Talking to a group of empty chairs, so this will be kind of an interesting situation. So we'll see how we go. And if we need to make adjustments as the semester goes on, then we will do our best to do that. And certainly if you have a suggestion, for example, one semester there was a coming through on the recording was a high-pitched kind of constant squealing noise that I couldn't hear, but it's only if you were on and watching, or if you were watching the recording afterwards. I had to go back and watch the recording and say, oh, that's terrible. So someone thankfully brought this to my attention. Should something like that occur, please don't hesitate to let me know, because high-pitched squealing noises are not in anyone's best interest. So let's get started. And let's see, I can do this. Can I do this? Where are we here? Yep. Okay. All right. So we've got that. We've got this. Basic idea of the class. Basic idea. Basic setup of the class in terms of chronology and topics. Assuming you've all had 4A or some equivalent of 4A, you would remember that 4A is the study of motion. What laws are applicable to the motion of objects. And so in 4A, perhaps you learn something about Newton's laws and conservation laws like energy, momentum, and angular momentum. Possibly you maybe touched a bit on gravitation. If you had that with me, you did all 6 of those things, 7 of those things. And you were accorded the entire semester to explore the consequences of these laws. If you have had 4B, which is electricity and magnetism, then you will have spent the entire semester examining the consequences of the Maxwell equations, which are a set of 4 laws. And they fairly adequately, actually quite adequately, describe classical electrodynamics. And so you possibly spent the semester talking about Maxwell equations and the consequences of the Maxwell equations. Here in 4C, however, we have a slightly different problem. We have 3 topics to go through in one semester, and they are, I don't want to say they're completely separate from each other, but unfortunately, in the way we are going to have to attack them, they will seem completely separate from one another. Therefore, the first approximately 1/3 of the class will be the thermodynamics section. We'll take approximately 5, maybe 5.5 to 6 weeks talking about thermodynamics and exploring the consequences of thermodynamics and its laws. We'll then move into optics. We will look at the three main models that we have of optics. Well, we'll look at two more than the third one, but nonetheless, we'll take a look at all three, examine the consequences of those. That will be approximately another 5-ish weeks. We'll have first celebration after thermodynamics. We'll have the second celebration after the optics. The last 1/3 of the class, approximately, I'm trying to go by about 5-ish weeks per topic. I'm not going to land exactly perfect, so don't hold me to exactly 5 weeks. The last section of the class, be it 4 or 5 weeks, will be on modern physics, which will include special relativity. We'll have a week at least on special relativity and its consequences. We will then move into quantum mechanics and talk about the modern formulation, or at least the beginningly modern formulation of quantum mechanics, including the Schrodinger equation, the uncertainty principle, the wave functions, things like that. So, I guess I would say if there's things that you are interested in having brought forth in the class, then okay, sorry, just taking care of some pop-ups that are suddenly coming up here. If you're interested in a particular topic, then please don't hesitate to let me know, and that way perhaps we can spend a bit of time and figure out how to work it in. Into the class. So what we're going to start with is the thermodynamics section, and we're going to spend the first approximately 1/3 of the class doing this. And so, as I often like to do, we're going to start with the laws today. And as we go through the laws, there's going to be terminology that I'm going to want to define for you. So we start by doing this. So let's see, we start by doing this. I have tried my best to decrease the glare such that you can see this. I'm looking at it. It does seem like I can see it. I probably need to write maybe a little bit larger. So I will endeavor to remember that. I will, however, forget every now and again. So if I need to write bigger, then my suggestion is one of you folks who's here now, I don't know how you do that. Maybe start talking so I know you need something from me. I don't know. Like I said, it's just kind of a work in progress. Laws of thermodynamics. Okay. There are 4 of these laws, and we will take them in numerical order, and you will see that that is a relatively strange thing to do. So we begin with law 0, and right away I've already forgotten to write a little bigger. Okay, maybe that looks okay. Okay, now law 0 was put forth as a law, I'm going to say around 1935. Incidentally, the chronology of this is not going to be the subject of any quiz or exam. It's simply for our entertainment, perhaps you would say. How's that looking? Oh, that looks, I think that's okay. All right. Okay, already I can tell I gotta need a shovel of ink. This is gonna be a fast job. Okay. This perhaps seems like a silly law. A little bit of glare happening right in the middle here, right on the word systems. Sorry about that. Not a lot I can do about that. I do have basically blinds down in this room and things covering all the windows as best I can in good scientific tradition. So this law may seem a little silly. Perhaps you maybe think it's superfluous. And you might be right. I think it's a fair thing to say that we take this law for granted, very much so. Um, I will also say that typical of thermodynamics, the laws are expressed verbally or in written language rather than with equations, such as Newton's first and third laws are. Newton's first and third laws, in case you didn't quite clue into that when I said Newton's first law is the idea that an object is going to continue in its motion unless acted upon by a net external force. But there's no equation that really is going to say what I just said, right? And the same is essentially going to be true with the thermodynamics laws. So here we have, if two systems are individually in thermal equilibrium with a third system, then the two initial systems, these two, are in mutual thermal equilibrium. So for example, I have, well, you can't really see this, but for example, suppose I have, right, I have my water bottle over here, and I've got the roll of paper towel here. So here are, for example, two systems. Well, we will, by the way, define what this terminology means. And here, for example, is a third system. So the idea being here that if these two systems, right, here's my water bottle and here's a balloon. If I say the balloon and the water bottle are in thermal equilibrium with each other, and we'll go through in a minute and talk about how we might know that. And then I say, oh, I'm going to take this balloon and I'm going to see, is it in thermal equilibrium with the paper towels? And I find that it is, in fact, in thermal equilibrium with the paper towels as well. Then what I should be able to say is, these two things together are in thermal equilibrium. Should I put them into thermal contact, then I would be able to say they are in equilibrium with each other, thermal equilibrium. Okay. So let's go through and take a look at some of the words that are in here and give them a little bit more precise definitions so that we can talk about them later on. And the first thing we're going to do is look at the word system. For example, what is a system? A system essentially is that part of the universe with which we are interested, right? With which we have an interest, in which we have an interest. Oh, remember, bigger writing, bigger writing. Hold on, I'm getting there, getting there. All right, hold on, I'm getting there. Okay. This may sound a bit grandiose, but ultimately, yeah, this is the universe. The stuff that we have is part of the universe. So might as well, universe is the biggest possible system. So let's just use that. The part of the universe in which we are interested. Okay. So for example, that could be the air in the balloon that I just showed you. It could be the air in the room that you are in. It could be the plasma in the middle of a star's stellar interior, in the core of the star. It could be the radiation from that star. It could be the radiation from a light bulb. We might be interested in that. It could be, for example, the set of water, liquid water, and water vapor that exists above the ocean in a meteorological sense, right? We have the ocean water, and then we have an air water vapor mix above the ocean. We could be interested in that. That's a two-phase system. It really is a situation where the system is the thing that you want to investigate. So I think that you can see thermodynamics is widely applicable. And in the way that the laws are crafted, they take on very widespread meaning. They give boundaries to what we're going to study, no matter what the thing is, no matter what the system is that we pick. The system that we pick is going to be separated from the environment by a system boundary. Let's talk quickly about that. Okay, the system is, we are going to separate the system itself that we're looking at. We're going to separate that from everything else by putting a boundary around it. Surrounding, is that, yeah, it's not too bad. Environment. That one does not seem to be showing up. I'm not super happy with how that red is showing up. So we're going to move back to blue. Okay, the system boundary is exactly what you think it is. It's just a real or imaginary boundary. In other words, if you think about the ocean example I told you about, the liquid water has a boundary, right? And okay, there it is. So it's a naturally formed boundary. And then above it exists the air and the water vapor mix, or perhaps also a droplet mix as well. But the idea being that there's a natural boundary to it. Okay. And you might say the same thing if I took, for example, a little pitcher of water here, right? There's a natural boundary to the water extent, right? The system. If my system was the actual liquid water, it has a natural system boundary to it. The system boundary can also be imagined. And this is pretty interesting. I could imagine just this piece of air right here, this piece of air. What I'm going to do in my mind then is I'm going to take this trash bag and I'm going to say, all right, imagine that I just put this around the air, right? I put this around the air and I'm thinking about the air that's in this bag, even though the bag's not really there. Right? It's just, you can just kind of imagine that it's here. And I want to think about what this parcel of air is going to do, maybe as it's a little bit warmer than its environment. So it's going to start rising and then things are going to start condensing or evaporating, right? The composition is going to change. Maybe it's going to then change with a little bit of wind input or something like that. So thinking about a boundary might be something by which you are putting your own boundary into it, or it might be something that you could use a boundary that already exists. All right, so this could be an imaginary or real boundary. All right, but it's the thing that separates our system from the environment. Now, the question about the boundary is, what kind of properties does the boundary have? The boundary can, for example, we'll take a quick example. Maybe it can let heat pass through. Can heat be transferred through the boundary? If heat can pass through the boundary, then we call it diathermal. Okay. We could also say, no, I'm not going to let heat pass through this boundary. I'm going to have a thick layer of insulation. For example, you're thinking about the air in the room that you're in versus the air outside. I mean, I assume you're in a building right now. That may not be true, but I am. So I'm going to think about the air inside the room that I'm in versus the air that's outside the room. And I'm going to say, well, I've put a big layer of insulation. It's a thick, there's bricks, there's some cotton batting, there's stuff in between them, there's drywall between this air and that air. Okay. So again, I have a natural system boundary, but I also might be able to say, well, heat doesn't really go in or out through that boundary. Okay. In that case, we would call that boundary adiabatic. Okay. We call that adiabatic. Is that showing up? Okay, that looks all right. So if we're going to think of a system, then we have to think of the ways in which the environment can interact with the system. And so in these ways of talking about, well, can heat pass through or not pass through? I'm talking about how is the environment able to interact with the system and vice versa. How is the system able to interact with the environment? If I do not allow heat through the system boundary, then whatever's going on inside or outside, heat is not coming in and it's not going out. Okay. Uh, and that means that I don't have to worry about that mode of energy transfer. Now, you'll see in a minute that there's another way to get energy through a system boundary that's not heat, and we'll talk about that. Nonetheless, this is one way, and those are the terminologies for that. Let's talk quickly about thermal equilibrium. That was another, in the zeroth law here, I talked about thermal equilibrium. So let's do this. Thermal equilibrium. All right. So what is thermal equilibrium? Well, I'm going to take two systems and I'm going to put them into thermal contact. Okay. What does that mean? That means the boundary between those two systems is not going to be adiabatic, because if it was, then the heat wouldn't be going back and forth, right? So thinking of thermal equilibrium means I probably have a diathermal boundary. So essentially what's going to happen, I'm going to take the two systems, I'm going to put them into thermal contact, and then I'm going to observe. If they are in thermal equilibrium, I need to be able to observe that they're in thermal equilibrium. How do I observe that? Well, go back to the balloon example here for a sec. Okay, so I had this balloon. Okay, and I said, well, I'm going to put it in thermal contact with, I know this is not a very good example. Maybe this is a glowing hot piece of metal or something, and I'm just holding it because I have no pain receptors, whatever it is. So suppose I put the balloon in contact with it. Suppose there's heat flowing between the two. How would I observe that there's heat? Say, suppose heat's coming into the balloon, right, from this glowing red hot piece of metal. I'm going to put the metal in contact thermally with the balloon, and I'm going to say, okay, now I can see that they are not in thermal equilibrium because the balloon's probably expanding, right? If the balloon has heat transferred into it, its temperature is rising, and then possibly it's going to expand. Okay, so I'm going to say there's a way for us to observe that something's not in thermal equilibrium, right? It's changing something. However, if something is in thermal equilibrium, then what's going to happen is its state should be constant, right? Its physical state should not change. between the two objects. Their physical states shouldn't change. If they transfer heat, then you would say, well, wait a sec, maybe the temperature is going to change of one or both, right? If there's heat coming in from the environment, or these two systems are exchanging heat somehow, well, then the temperature of this one might be dropping, the temperature of this one might be increasing. We don't, okay, something's happening. For example, I drop ice into liquid, ice cubes into water. The temperature of the ice cubes may not be changing, but we will see them possibly shrinking, right? So that would be, oh, wait a sec, these are not in thermal equilibrium with each other. So thermal equilibrium happens when the state variables, what are called the state variables, are things that describe the state of the system, right? So we're going to say when the two systems are in thermal contact, and their state variables do not change. Bigger writing, bigger writing. Their state variables. Okay. So we've kind of talked about what thermal contact means. The question now is, what are state variables? Okay, you can see this is a multi-runged ladder of terminology. Every time I try to define a term, I introduce another one, which I then have to define again. Okay, so we're going to keep going with this for a little while. Thermal contact, I think we can define that fairly well by the idea of what is the boundary, right? If they're in thermal contact, the boundary is diathermal, so heat is able to get between them. But that means now their state variables, when in thermal equilibrium, their state variables do not change. So what are state variables? They describe appropriately, or they are chosen appropriately, such that they describe the state of the system. Okay. What does it mean by appropriate? Well, I'll show you in a sec. Appropriately chosen quantities describing the state of the system. What does this mean? Well, for example, if it's a gas, maybe you're interested in the pressure and the volume. Okay. If it's a liquid, maybe you're interested in the surface tension and the surface area. I mean, like I said, you could also be interested in other things, right? If it's the gas, maybe you're interested in, for example, the density of the gas. I'm just giving up examples. That's what I mean by appropriately chosen. What is it that you're trying to investigate about the system? That's going to that's going to inform your choice of what the system variables are going to be. Okay. So for example, for this, we are going to get rid of these. Okay, such as if your system is a gas, perhaps you're interested in the pressure and volume. Okay, by no means should you take this as this is always the thing and this is the only thing and this never changes. Like I said, it depends on what we're trying to investigate about the gas. But for example, pressure and volume are two state variables in the gas. Liquid. What did I say? Surface tension. You might be interested in the surface tension. You might be interested in something completely different. Maybe you're interested in the area of the surface of the liquid. Okay, maybe you're not. Who knows? What if it's, for example, radiation? What if the system we chose is the radiation coming out of a light bulb? That's our system. Our system is that radiation. You can do this, right? This is part of the universe. Remember, system is whatever part of the universe we're interested in. So we might be interested in the radiation. The radiation you might have an energy density. You might have something like a radiation pressure. If you didn't know that radiation can exert pressure, well, maybe you do now, and we'll investigate that a little bit more later. So appropriately chosen, okay, such that you are on the road to trying to investigate what it is you want to investigate. All right. One more word about the state variables, and then maybe we can move on to the first law. The state variables are linked usually, and I say usually, but for us, always, they will have an equation of state. Okay, the state variables will be linked by an equation of state. Okay, an equation of state. For example, if I'm dealing with an ideal gas, the equation of state of the ideal gas would be an ideal gas PV equals nRT, the ideal gas model. That's the equation of state of an ideal gas. It turns out that we will use the ideal gas quite a bit as a backdrop, as a system. Why? It's simple. It has only one phase, right? It's only a gas, never has become a liquid. If it's an ideal gas, it can't become a liquid. And it's relatively, I already said relatively simple, and it's homogeneous usually, right? So if we have a simple system by which we can apply the laws, it becomes a little bit easier to see how to apply the laws and how to use them. So this is what we're going to do, and use the ideal gas as a fairly straightforward system to investigate. All right, let's see. Is that everything I want to say about the zeroth law? Oh, I got one other thing about this. Oh, definitely need this. Law 0 gives us the ability to define a temperature. Okay. It gives us the ability to define an empirical temperature. Here I've gone and done it again. What does empirical mean? Empirical temperature, okay? An empirical temperature remember how I had the balloon and the red hot piece of water bottle? So I'm going to put these in contact with one another, and I'm going to say, oh, well, if heat's getting transferred, they're not in thermal equilibrium. The temperature of this is rising. How would I know if the temperature of this is rising? We talked about it expanding possibly, yeah? Or if I cooled it, it would contract. So what I'm going to do then is say, oh, okay, at the temperature, no, what I'm going to do is say at this size of balloon, the temperature is 14. It's 14 ballooniuses, right? That's my new temperature scale. And if I put it in contact with something and all of a sudden I find, oh, now all I got to do is measure the volume, and then I say, oh, there's a monotonically decreasing function here, or increasing if I go the other way, such that I can relate the volume of the balloon now to what the temperature is. And now the temperature is only 10 ballooniuses because the ratio of volumes tells me that it's 14 to 10. Okay, or something like that. That's what an empirical temperature is. I'm actually using something else to tell me, okay, I'm going to now define a standard and say, this is what this temperature is, and now I'm going to grade it, right? And say 0, 1, 2, 3, 4, 5. right? And I'm going to say every step is 1 degree, and that means it's warmer or colder if I go down, et cetera, et cetera. That's an empirical temperature. That's what this law kind of gives us the theoretical ability to do. Well, by the way, which is kind of ridiculous because we've been taking the temperature of things since like the 1800s. So by 1935, we finally figured out, hey, we can make a temperature. We know what one is. We still don't really know what one is, but that's okay. We at least have the ability to define one. Okay, so that is the situation with the definition of an empirical temperature. So, for example, if I have right my material A over here, and I have material B over here, and I take my balloon and I say, okay, when I have the balloon in thermal contact with A, here it's got a size that looks like this. The volume of the balloon, we'll call that volume A. Okay, then I'm going to take the balloon and I'm going to put it in contact with object B over here. I'm going to measure its volume when it's in contact with object B over here, and I'm going to say if VA equals VB, then I'm going to say the temperatures of A and B are equal, right? All right, then my temperature of A equals my temperature of B. That's basically what the zeroth law tells us. And so after this, we're not going to spend a whole lot of time on the zeroth law. That's pretty much everything we're going to talk about the zeroth law. So there you go. We're now moving on to the first law. Okay. So we have set concepts onto somewhat firmer footing, concepts such as what is a system, what is thermal equilibrium, what is an empirical temperature. We have the ability to define those things. We know we need state variables. We know we need equations of state. We know we need all these things. That's kind of what the zeroth law does for us. In practice, we're never going to return to this. All right. We're not going to see the zeroth law again. It's just foundational. Okay. Most of our time, in fact, all of our time in this class is going to be spent on law number 1 and law number 2. So we will get to those right now because they're kind of important. First law. Can I not write of thermodynamics after it? First law of thermodynamics. You can write that. I'm going to tell you to write it, and I'm not going to write it. You already have worked a little bit with this, but only in a mechanical sense. If you have taken Physics 4A, which you should have, because that is a requirement for this class. So we've talked about energy conservation mechanically, right? Oh, the object falls in a gravitational field. It loses some of its gravitational potential energy. It gains some kinetic energy. It hits the desk. It gives up its kinetic energy into thermal energy. Okay, all sorts of types of things like this. Essentially, that's what the first law of thermodynamics is. It's energy conservation. However, since we've already kind of dealt with all the mechanical bits of the energy conservation, let's take those as, okay, we know those are conserved and we know how to deal with them. Let's push them aside for a little while and look at now with energy conservation. What else are we talking about? We have a system. We can transfer heat into the system. How does that affect the energy of the system? Okay. Well, it didn't increase the potential energy of it. It didn't increase the kinetic energy of it because it's still sitting here. So what's going on? Well, now we have another quantity, which is called the internal energy of the system. Okay, so we're going to talk about the internal energy of a system. Internal energy of a system in practice could be, and by the way, this is not kosher thermodynamically, but and I'll tell you why in a minute, but it could be the speeds of the atoms or molecules. It could be the potential energies between them, right? It's microscopic. It's the microscopic energies that we're thinking about. It's the thermal energy, it's the bond energy, it's right, that kind of microscopic kinetic and potential energies. Rather than the macroscopic ones, rather than the system actually as itself, it's a box of air falling down. No, nobody cares about that. We just want to know what's going on to the actual internal energies, right? That's what we're going to concentrate on here. The internal energy of a system can be changed. How can it be changed? Well, oh, I erased it, but it was over here just a little while ago. I could transfer heat in or out, right? The system can exchange heat with its environment. So we call that heat transfer. Also, the system itself could, like the balloon, expand. When it expands or contracts, work is done on it by the environment or on the environment. Okay, so this is going to be the internal energy of the system can change via work or heat. So I should say and or heat. So that's really what I should say. And or work. And the work can be done by the environment or on the environment. Notice I didn't tell you which way the heat transfer was going, so I'm also not telling you which way the work done is going. We'll go over the sign convention in a minute. All right. Essentially, if I want to write this down as a fairly straightforward thing, I would say that the change in internal energy, I'm going to use INT for internal, is a result of heat transfer, which will universally be the symbol capital Q. And the work done, which is universally the symbol capital W. Like so. Okay, so the change in internal energy. So this is the expression of our first law of thermodynamics here, microscopically, with the heat and work changing the internal energy. So the question here is, how does work change the internal energy? Can work change the internal energy of a system? Absolutely, it can. And I'll just do a quick description here to show you what I'm talking about. This should be coiled, actually. Okay, so imagine here. Oops. Imagine here I've got a vat of liquid. Okay, maybe I've got a barrel of liquid, water. I'm going to put into it this paddle wheel. I'm going to actually erase these because it doesn't look like it's coming through very well as a diagram. Okay, so it's a barrel full of liquid, and I've put into it this paddle wheel. And the paddle wheel has a coiled string around it, and I've attached it to a pulley with a mass. I'm going to let the mass go, which means the mass is going to drop. It's going to unspool from the coil here, and it's going to rotate the paddle wheel. Is heat being transferred? I think the answer is no. Is work being done on the liquid? I think the answer is yes. Do you follow that? As this drops, right? I know we weren't going to talk about mechanical energy. It loses gravitational potential energy. That energy goes into turning these paddles. What is the effect of the turning of the paddle wheels on the liquid? It probably heats it up. It increases its temperature. If I'm going to be really careful with my terminology, it increases its temperature. No heat is transferred, but notice that work is being done and the internal energy of the system is changing, which means in this case, its temperature is rising, but no heat is being transferred. Here is I'm bringing this up early because I want to immediately strike. Many times I find people have an association with heat and temperature. They are not the same thing. So I'm trying to strike between those two things, get them separated in your minds. Heat is a transfer of energy, of thermal energy. Temperature is an indicator of the internal energy, at least for us, for an ideal gas, our system, okay? I don't need to transfer heat to change the temperature. That's what this thing is telling us, right? That's what it's doing. It's telling us I can do work and change the temperature, okay? So be aware of that. So note, if this does increase the temperature, okay, that's fine. Maybe it increases it, but I did a certain number of joules of work on it. If I were to increase the temperature of the liquid the same amount by using heat, how much heat would I have to put in order to get the same effect in temperature change as I just did with the work? Turns out it's not the same. It's a different amount of energy. Heat in the 1800s was measured in calories. Okay, and you know what calories are? Well, maybe you don't. Oops, joules. Work is measured in joules. Okay, there is a mechanical equivalent to heat, right? There is a mechanical equivalent to the heat. I can do work on an object, increase its temperature. I can transfer heat to an object, increase its temperature the same amount, but I've done different amounts of heat and work, okay? The mechanical equivalent of heat, that is to say, how much, dang it, I have to, well, that's okay. I think you can see that. Mechanical equivalent of heat is is 4.186 joules for every 1 calorie. So I have to do 4 times the amount of work to rise the temperature by 1 heat transfer of a calorie transfer, right? If I put 1 calorie of heat in, I would need to do a little over 4 joules worth of work to do the same temperature rise. Okay, so that's the conversion between these two things. They both can change a state's variables. Okay, that's what this is telling us right here. This internal energy is a state variable. This is changing if I transfer heat or do work. Note that neither of these is a state variable. We'll get back to that later. Neither one of those is a state variable. Okay. Bar charts and whatnot will be very useful. So if I were to draw a bar chart for this, you would notice that I said, well, I've got all this potential energy here. This might be the GPE, the gravitational potential energy of the mass, right? As it's up here before it falls. But then after it does fall down a certain distance, right? Where has that energy gone? Now it's internal energy. It's internal energy in the liquid. Okay. And if you wanted to say, well, the internal energy of the liquid already existed beforehand, okay, fine. That just means I've got a box up here in which the internal energy of the liquid was before it. E internal, say initially, and now this is E internal finally, right? So it's still the same amount of energy, and energy does have to be conserved. So my bars have to be the same size, and I have to know where the energy's gone and what form it's gone into. Otherwise, I've violated energy conservation, and that's a problem. Okay. Let's get on to the second law here. That's the first law, energy conservation, but thinking of it on a microscopic scale. Let's get on to the second law here. Hopefully we'll have enough time for the second and third laws. All right, second law. Of thermodynamics. Maybe you don't need to write that because it's kind of obvious, I guess. Okay, this is going to be an interesting one, perhaps. Second law here. Oh, I forgot to tell you the first law, 1850. The chronology of the law of first law, about 1850. The chronology of the second law, about 1824. So you'll notice we went from the zeroth law, which was 1935, to the first law, which was 1850, to now the second law, which is 1824. We're going the wrong way in time, but we're going the right way numerically. Okay, who knows what the heck's going on? There's a great story behind all of this, but we are moving on right now. Nonetheless, in 1824, we were granted, we were given wonderfully a statement from a French scientist and engineer named Sadi Carnot. And so Carnot's statement of the second law Carnot's second law. Okay, so I'm going to write you what Carnot's second law is, and I take the liberty of calling it his law. I need to go over here. Wait a second. Okay, so it's a cyclic process whose only result. Oh, can you read that? Let's see here. I'm going to stare at you for a minute. Yeah, I think that's okay. I could write a little bit bigger though. Okay, I'll try that. Not quite done. A cyclic process whose only result is to exchange heat with fewer than 2 heat reservoirs. And sorry, there's glare right in the middle of the word reservoirs right there. Reservoirs. And produce work. Is impossible. Okay, that's the Carnot statement of the second law. Couple of other quick updates on what the terminology here means. A cycle, okay, a cycle means I've taken a system through, I've changed its state variables. I've taken it through a process and then another process and another process. Every process changes its state variables. But a cycle means I have returned the system to its original state. I started here, I changed its state variables, I changed its state variables, I returned the state variables to what they were initially. That's a cycle, no matter how you do it. I go here, 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 and I'm back here. That's a cycle. Okay. So this means the state variables are returned to their original values. Okay. So I heat something, compress something, transfer work, heat, transfer work, blah, 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 and then I do it all backwards and I return everything back to where it started. Okay, that's what it means. Okay, so a cyclic process whose only result is to exchange heat with fewer than 2 heat reservoirs and produce work is impossible. That means heat reservoir we need to define. A heat reservoir is essentially like the ocean. Okay, it's something by which we can transfer heat in or out, and it doesn't really change the temperature of the ocean that much. I could take a cup of boiling water, throw it in the ocean, measure the temperature of the ocean, go, yeah, that didn't really make a big difference. Okay, I could take some ice cubes, throw them in the ocean, measure the temperature of the ocean, same thing, right? That's a heat reservoir. Okay, so what Carnot is saying is if we want to produce usable work, we have to have at least 2 heat reservoirs in play here. One from which I am receiving hot, like a heat transfer out of a hot reservoir, and then I have to dump the rest of it into a cold reservoir. Okay? Our cold reservoir is typically the atmosphere. When you drive your car, or you yourself are a thing that produces heat, right? You take heat from your heat reservoir, which is when you eat food, you burn, you're slightly warmer on the inside, right? You have an internal temperature which is warm. Where are you dumping that heat? Into the air, right? You are exchanging heat, 1 out, 2 out, right? So, and you produce work. But note the use of the word impossible. This is why thermodynamics is so powerful. How many other physical laws have the word impossible in them? I can't think of many. I'm about to show you another version of the second law, which does also have the word impossible in it. But that's a really powerful thing, to see the word impossible. You cannot do this. So diagrammatically, here are some cycles which cannot, according to Carnot's statement, cannot exist, right? So, let's do this. Forbids. Okay, it forbids. Okay, so this law forbids a cycle, which I'll just diagram as a circle, just because it's that's something that's returned to its original state. And let's suppose work is coming out. I have a cycle, and all of a sudden I've gotten work out. That's forbidden. I haven't exchanged with at least 2 heat reservoirs, right? Note also that this is certainly prohibited by the first law, because if I have undergone a cycle, what is the change in my internal energy? Well, remember, internal energy is a state variable, and the state variables have been returned to their original values. Oh, you can't really see that. It says original value. Sorry, returned to original values, which means the change in the internal energy is 0. And by the first law, that the change equals Q plus W, if I suddenly get work out and it's equal to plus 0 equals 0, right? First law forbids this one also. Okay, first law forbids, for example, this one also. Oops, nope, this way. We'll do this. Here's a cycle. Work, heat, like so. First law will forbid that one. The arrow on the heat is going up. You can't see that very well, so I'll darken it in. Maybe now you can see it. There we go. Oh, here's a cycle, here's my system, and it's producing work and giving off heat, yet its internal energy is not changing. That would be forbidden by the first law also. So you say, what use is this? Why are you telling us about all of these things which are already forbidden by the first law? Well, here's one that's not forbidden by the first law that is forbidden by the Carnot statement. All right, here's my heat reservoir at temperature T. Q that way, cycle work out this way. That is not prohibited by the first law. Q comes in, work goes out. If I just say the first law, Q is equal to W, first law says fine. But this is prohibited by the second law of Carnot here. We have exchanged heat with fewer than 2 heat reservoirs. So what is allowed by Carnot's statement? Here is, I'm going to label this H. Oh, you know what? Sorry. Yeah, that's fine. So this is also forbidden. What's allowed is this one. Allowed. Allowed is this, right? I'm going to label this H for hot. Right? So I'm going to take this cycle here, and I'm going to say, I have to dump excess heat. I have to dump excess heat, right? Just like I was telling you, we dump excess heat into the environment. So this is allowed by the Carnot statement. I have 2 heat reservoirs, and I'm producing usable work. This is allowed. First law does not prohibit this one. First law doesn't prohibit this one. Carnot prohibits this one, but allows this one. Okay. I don't have a lot of time left here. So I was going to introduce you to the Clausius second law statement. Maybe we'll take a minute to go through that next time, because I want to finish off by going through the third law really quickly right now. And then I want to have a few closing statements, and then we'll be done for today. So let's do the third law. Third law. Like I said, law 3 and law 0, we are going to spend basically this is going to be it. This is all your time you're going to see. The 0th law or the third law is just from today. First and second are what we're concentrating on almost exclusively, not almost, exclusively this semester. The third law is essentially due to a fellow by the name of Walter Nernst. Oops, I can't spell his name though. Nernst and Max Planck. So it's called the Nernst postulate or the Planck theorem, whichever you like. But effectively what it says is, as the temperature of your system decreases from a non-zero value, it decreases, decreases. There is no, say, a couple of more things that we would have to define. There's no reversible adiabatic way of taking a system whose temperature was initially not 0 and making the temperature 0. Now, when I say 0, I don't mean freezing, right? I'm talking about 0 on the absolute scale, which, by the way, I didn't have time, but effectively the Carnot statement allows us to define a thermodynamic temperature. The thermodynamic temperature is the Kelvin temperature. Okay, we're going to use the Kelvin temperature as the thermodynamic temperature. Whereas the empirical temperature would be the Fahrenheit or the centigrade scale, right? Those are empirical temperatures. The third law essentially is the statement of unattainability. Ooh, unattainability. In other words, I'll spare you the full statement of the thing here. cannot reach absolute zero temperature. Yeah, my pens are running out. Sorry about that. That you cannot reach the absolute zero temperature. Okay, that's a statement of the unattainability of it. So those are the four laws of thermodynamics: 0, 1, 2, and 3. Interestingly, this was about 1910. So you'll notice that in chronology, the second law came first, the first law came second, the third law came third, and the 0th law came last, which is why it's the 0th, because it's foundational, and you couldn't call it the first because the first had already been around for like 85 years. Everybody knew what the first law was. So you can't undo that. So they had to go back and say it's the 0th. Anyways, a little bit of fun trivia there. We're going to wrap it up. Now that you have at least the beginnings of the laws of thermodynamics behind you, I want to read you a couple of quick statements about thermodynamics and its power, essentially. For me, this is the greatest subject of physics, and it's so because of its applicability widely, right? Notice that we've never included the atomic hypothesis in this, okay? Thermodynamics makes no assumptions about what your system is composed of, okay? It doesn't at all. No, not to say we're not going to talk about it. We will, but that means we're a little bit outside of classical thermodynamics, okay? So Einstein says thermodynamics alone amongst the physical theories will never be overthrown. Note that this was a guy who overthrew Newtonian mechanics, okay, and gravitation. Okay, so not a small statement there. Never be overthrown. Arthur Eddington, the astronomer, says the law of entropy increase, which is related to the second law. The second law, entropy increase, holds the supreme position amongst all laws of nature. The second law. Okay, we will spend time talking about that. I even jotted down my own statement here. Thermodynamics is deeply beautiful and subtle science whose depth of consequence cannot be revealed in a mere 5 weeks. And that, to me, is the problem with this class. It's painful for me to try and reduce thermodynamics to something that I can get across to you in 5 weeks. What that means is I can't get it across to you in 5 weeks, and we'll just both kind of agree that we did the best we could. So we'll spend some time working through this. I hope that at certain points in this class, you can see the subtle beauty of this subject, because this is a near and dear subject to my heart, and we don't even get the full semester of it. And so with that, I will say happy rest of your first or second day. It's actually the second day of classes here, but happy end of first class for us. And I hope you go forth and enjoy the rest of your day, wherever you may be. We will pick this up again tomorrow, and I will talk to you all then. All righty. Thanks so much for your attention. See you then.